गुड मॉर्निंग. आज आपल्याकडे एक फार मोठी व्यक्ती फिजिक्स, अलीकडं आपण बरेच सारखे प्रोग्राम्स करतोय. 2 months ॲगो त्यागी सर IIPTचे चेअरमन आपल्याकडे व्हिजिट केले होते. त्यानंतर विजय सर आले होते आपल्याकडे फिजिक्सचे. आता आज जे इंडियामधलं सर्वात जे काय IITच्या नंतर आपण ज्याचं एक ग्रेडेशन देतो, बिर्ला इन्स्टिट्यूट ऑफ टेक्नॉलॉजीज, तर त्या पिलानीमध्ये त्यांनी बरीच वर्ष काम केलेलं आहे. कारण सुरुवातीला फक्त एकच कॉलेज होतं बीट्सचं. त्यानंतर मग बीट्स गोवा कॅम्पस, हैदराबाद कॅम्पस आहे. प्रेझेंटली ही इज वर्किंग ॲज अ प्रोफेसर इन बीट्स गोवा. आता त्यांचं एज 66 years आहे. स्टील ही इज बिझी इन टीचिंग, म्हणजे लेक्चर्स घेत आहेत. फिजिक्समध्ये फार मोठं काम निश्चितपणे बीटसाठी केलेलं आहे, देशासाठी केलेलं आहे. आणि बऱ्याचशा जे काय ऑलिम्पियाड एक्झामिनेशन्स आहेत, नॅशनल असेल, ACN असेल, तर त्या ऑलिम्पियाड एक्झामिनेशनचं जे काय लिडरशिप आहे ते देखील, किंवा त्या स्टुडंटना गायडन्स, अशा टाईपचं अतिशय सुंदर काम त्या सरांनी केलेलं आहे. त्यामुळे ती व्यक्ती आज या ठिकाणी आलेली आहे, त्याबद्दल निश्चितपणे संस्थेचं आणि आपलं सर्वांचं मी भाग्य समजतोय. आणि आज थोडंसं येताना मला आणखीन एक म्हणजे अभिमान वाटतो की ही इज केम विथ हिज मदर अँड वाईफ, की ज्यांनी इतक्या ह्या एजमध्ये देखील सोबत त्यांच्या ठिकाणी आलेत, आपल्या संस्थेला व्हिजिट होते. त्यामुळं निश्चितपणे त्याचाही या ठिकाणी आनंद आपल्याला संस्थेला 100% आहे. तर आज क्वांटम फिजिक्स ह्या सब्जेक्टवरती थोडंसं जरा सर आपल्याला गायडन्स करतील. क्वांटम फिजिक्स हा जो काय म्हणजे इट इज अ सी, समुद्रासारखं ते इतकं ते मोठं विस्तृत असं तो सगळा सेक्शन आहे की ज्या क्वांटम फिजिक्समुळं जे काय आपलं सध्या प्रचंड डेव्हलपमेंटचं आपण जे काय बघतो, आपण जगाची डेव्हलपमेंट म्हणू त्याला आपण, कॅम्प्युटर वर्ल्ड विदाऊट क्वांटम फिजिक्स कॉम्प्युटर वर्ल्डची डेव्हलपमेंट होऊ शकली नसते. किंवा जेवढे आपले टेक्नॉलॉजी जी डेव्हलप होत गेलेली आहे संपूर्ण जगभरामध्ये, तर त्याच्या पाठीमागं बेसिक रिझन हे क्वांटम फिजिक्स आहे. आणि त्यामुळं मेडिकल सेक्टर असेल किंवा इंडस्ट्री असेल, सर्व ठिकाणी आपण सकाळी उठल्यानंतर जे काय ब्रेड वगैरे आपण रोस्ट करतोय ना, तर त्याच्यामध्ये देखील प्रिन्सिपल क्वांटम फिजिक्सच आहे. म्हणजे प्रत्येक क्षेत्रामध्ये क्वांटम फिजिक्सचा यूज हा मोठ्या प्रमाणात, म्हणजे सायंटिस्टने जर याच्यावरती वर्क केलं नसतं किंवा त्यांना ते लक्षात आलं नसतं, तर डेफिनेटली आपलं जग हे निश्चितपणे जे काही डेव्हलपमेंट आता आपण पाहतो त्याला निश्चितपणे ते मुकलं असं म्हणावं लागेल. त्यामुळे इतका मोठा स्टडी ह्या क्वांटम फिजिक्सवरती केला गेलेला आहे. आणि त्या क्वांटम फिजिक्सचा जे काय म्हणजे जी माहिती आहे किंवा त्याचं जे काय नॉलेज आहे, सर तुमच्या या ठिकाणी शेअर या ठिकाणी करतील. आणि त्यामुळे निश्चितपणे तुम्हाला देखील एक वेगळ्या प्रकारचा इंटरेस्ट त्या क्वांटम फिजिक्सबद्दल निश्चित होईल, किंवा काय त्याचं ॲक्च्युली त्याचं विस्तृत स्वरूप आहे ते तुमच्या त्या ठिकाणी ते लक्षात येईल. तर मी सरांना या ठिकाणी इन्व्हाइट करतो की त्यांनी या ठिकाणी आपल्या विद्यार्थ्यांना गायडन्स करावं. थँक्यू.
Well, first of all, the students, I'm very grateful for your presence here, and I hope I'll be able to tell you something that will be useful to you in developing your careers. But then most importantly, I would like to thank Mr. A.R. Tambe, who has taken the initiative to reach out to people like me from eminent institutions like BITS and so on. And I think our friend Biplab Paul was constantly in touch with me, trying to get me to arrange this program, and he was constantly asking me when I'll be free and what I'll be doing and so on. So finally it all worked out that I was able to come yesterday, and then had some trip in Kolhapur, came back, and today morning I'm here with thanks to Mr. Paul. I'm also grateful that Shreya madam, Sangeeta madam is present here as well, and of course Mr. Abhishek Tambe is here, I'm grateful to him as well. And then, of course, Shushti Tambe is also here. So I'm grateful to all these distinguished people. And I've just learned that Mr. A.R. Tambe is a very visionary leader, and he has been able to build this wonderful institutions, ensuring that all the appropriate values are incorporated in the running of the institution, as well as in trying to build your character. I must point out that even more than knowledge, character in the modern world is far more important, and one should never lose sight of that. Thank you very much. So let me begin with today's talk. It's called the quantum world, and I want to compare it with everyday world. The whole idea that everyday world follows a certain set of rules and quantum world follows a different set of rules. So a few things I would like to talk about that. So in today's talk, as I mentioned, everyday physics, that means what you observe in front of you, with some exceptions, is well described by classical mechanics. So I hope you all know what classical mechanics is. Classical mechanics is the mechanics that is based upon the Newton's laws of motion. Okay? And so that's why it's called classical. Then what kind of bodies would obey Newton's second laws? Bodies that are sort of big, like cricket balls, baseballs, and so on. But there are certain objects which may be called as microscopic or subatomic particles, such as electrons, protons, etc., which do not obey the laws of classical mechanics. They obey the laws of quantum mechanics. And since many applications involve flow of electrons and electric current and conductivity of materials and so on, all of these things depend upon the properties of electrons, which are at the root quantum mechanical. So without understanding quantum mechanics, it's very difficult to design devices or make use of these laws of physics to actually build useful applications. So there are fundamental differences between the assumptions, the predictions, and the experimental confirmations between classical mechanics and quantum mechanics. And this talk will contrast the two theories and highlight these differences. Okay. Well, in classical mechanics, there is a clear distinction between a particle and a wave. A particle is a particle. A wave is a wave. Okay? So, person from North India is North Indian. Person from South India is South Indian. North Indian cannot become South Indian. South Indian cannot become North Indian unless they live in these places for a very long time. But you see, particle remains a particle in classical mechanics. Everyone can say a cricket ball is a particle. There is no question about it. What does the particle have? It has mass. It can have momentum if it is moving. So these are some properties. It can also be spinning. The cricketers use spinning balls to confuse the batsman. So it can have mass, it can have spin, which carries angular momentum, right? And it can have linear momentum as well. It has energy. So these are some of the properties that can be associated with particles or solid objects. And all of these properties are there in classical systems as well. Waves, on the other hand, can also carry a few things. If supposing I have a laser beam hitting my thing, it's going to burn my skin. So what happens? The laser beam carries energy, right? And you can see that it also carries momentum. So waves can also have some of the mechanical properties, but they do not behave the same way. Okay? So a particle remains a particle and doesn't flip to become a wave. Okay? But a quantum mechanical object can be either a particle or a wave. That's the difference. Right? So how can something be one thing as well as the other thing when you cannot construct a mental picture of either of those things being together? You can picture one or you can picture the other, but you cannot picture them being the same thing at the same time. But in quantum mechanics, subatomic particles appear to behave in this manner. Okay? So here is one of the critical experiments which shows that in the classical mechanics, for instance, I've got a two-slit experiment, right? So S1 and S2 are two slits and light collimated and perhaps coherent light is passing through the two slits. And what happens? Their wave fronts intersect. but they intersect at different points with different phases. Okay, and you find that where they constructively interfere, you get a maximum, and where they destructively interfere, you get a minimum. So if you have put a screen in front of the two slits, I'm going to find a pattern of maxima and minima. So that is very clear as far as the waves is concerned. You can see this by dropping a stone on a placid water, let's say in a lake or something like that, or even in a bucket of water. You drop a small pebble, you will find circular waves going out. Right? You drop two pebbles and you can see that there is interference. So you can look at interference in a bucket of water. On the other hand, you can find that if I have a stream of quantum particles, not classical ones, quantum particles, and make them undergo the same two-slit experiment, you'll find that they seem to congregate in certain regions, and the regions in between those two regions, there are hardly any particles or no particles. Okay? So it is as if then that these particles also behave like interfere. They also behave like waves. Because waves interfere, but you've never heard of particles interfere. How would a classical particle behave? Well, a classical particle would have one set of particles going through one slit, another set of particles going through another slit, and I'm simply going to get two peaks, that's it. But here I get several peaks for quantum mechanical particles. So it was a surprise for people to learn that even electrons behave like waves. This experiment has actually been done 100 years ago. Okay? So there you go. What do we know in classical mechanics? The blue text is for classical mechanics. The black text is for quantum mechanics. Okay? Can you see the screen? Okay, good. So what we find? We find that particles have definite trajectory. That is, when I throw a ball, I can follow the path of the ball all through the points it passes before it hits the batsman. Okay, so that means so this locus of points which connects each point in its path is called a trajectory. Okay, so I can follow the trajectory. But quantum mechanics, no trajectories. All I know is that the particle is here at this time and a particle is somewhere at a later time. How did it go from here to there? I don't know. Okay, so a quantum mechanical, so you see, look at the energy for instance. When I have a wave, then there's going to be wave fronts. Just like, for instance, when I drop a pebble in a bucket of water, there's going to be ripples. Each ripple is a wave front. So how do you define a wave front? There's something called the phase. Right? The phase of a wave depends upon what its wavelength is, and did it start with a crest or a trough or somewhere in between. Okay? And then what happens? The energy of the wave is distributed entirely into the wavefront. Okay, so that's why the energy at any one point is not all the energy of the wave. But what happens with a quantum mechanical wave? What do I mean by quantum mechanical wave? When I say particles behave like waves, what people said is that a wave can be associated with the particle, and these waves are called de Broglie waves. You must have heard the term de Broglie waves. Okay, so it is the de Broglie waves that interfere and produce this interference pattern where particles are concerned. Okay, so this is what we have. We are going to have energy distributed in the wavefront in the classical mechanical systems. In quantum mechanical systems, a wave will start out almost exactly like a classical system. But as soon as the wave encounters an obstacle, such as an electron, suppose an electromagnetic wave interacts with an electron, then it appears that the entire energy of the wave is concentrated at one point corresponding to the point of collision. So at the point of collision, the entire energy of the wave is concentrated, and the interaction between the wave and the particle is as if there is a collision between two particles. So we say that the wave behaves like a particle when it interacts with matter. Okay, if it is not interacting with matter, it may still remain a wave. Okay, so that's the key difference between classical and quantum mechanics. Determinism, this is very important. Okay, what does it mean? Supposing I write down the equation of a particle in classical mechanics, and if I happen to know the initial conditions, what are the initial conditions? initial position and initial time. If I know these two quantities and I'm able to solve the Newton's laws of motion, then I can find out the position and momentum of the particle at any later time, both in the future as well as in the past. Supposing I know the position and the momentum of the particle at, let's say, t is equal to 1 second, then I can find the position and momentum for t is equal to 10 seconds as well as t is equal to minus 5 seconds. So in classical mechanics, prediction can be possible, retrodiction is also possible. That means I can predict the past. Okay? In quantum mechanics, that's not what happens. The equation of motion in quantum mechanics is the Schrödinger equation. Have you heard of the name Schrödinger equation? Good. So the Schrödinger equation has an unknown, which is a complex valued function called wave function. Okay? And the wave function can be defined at t is equal to 0. And if I solve the Schrödinger equation, then I can find out the value of that function at a later time, t greater than 0. I cannot find its value for t less than 0. So in quantum mechanics, prediction may be possible as far as the wave function is concerned, but retrodiction is impossible. That's the key difference between classical and quantum mechanics. Okay? So retrodiction is not possible. But supposing I know I have a knowledge about the wave function, does it tell me everything that classical mechanics tells me? The answer is no. All that the wave function does, it tells you what is the probability of finding a particle at some particular position. So that means the information that the wave function contains is probabilistic. Okay? So you might say that as far as the wave function is concerned, quantum mechanics is deterministic. But as far as the particle trajectories and positions are concerned, it is non-deterministic. So you might say that it is deterministic and non-deterministic almost at the same time. Okay? But because these two words refer to different things, there is determinism as far as wave function is concerned, non-determinism as far as particle or wave motion is concerned. If you have any questions, you can please stop and ask me. I don't mind answering the questions during the lecture. Okay? Another thing is called causality. What is meant by causality? Does anybody know? Can you guess what causality is? I studied hard and I passed the exam. So studying hard is the cause, passing the exam is the effect. Is that right? But supposing, can I say that the effect can happen before the cause? Not possible. So causality means that there is a chronological ordering of cause and effect. And there is one more thing. A particular cause can have a unique effect. Okay? If I jump out of a window, I'll break my legs. That's going to happen no matter what I do. So the same cause will produce the same effect. Right? If I eat good food, I'll be healthy. That's cause and effect. Okay? So in classical mechanics, if I make identical measurements on identical systems, I should get the same answer. I should get the same result. Okay? That's one aspect of causality. Okay? This also means that the same cause always produces the same effect. So we say that classical mechanics is a causal theory and causality is valid in classical mechanics. What happens in quantum mechanics? Doesn't happen. Identical measurements on identical systems do not give one answer. So they do not give identical answers. Okay? So what happens? There is a list of possible answers. Okay? And measurement seems to pick out one among that list. So this list of answers is what is called as allowed values of the measurement. They are called eigenvalues of the measurement. Okay? So any measurement on a set of identical systems will actually produce different results for different systems. Okay? So what does it mean? It simply means that in classical mechanics, when I say that the mass of the cricket ball is say 100 grams, then that 100 grams is associated with that cricket ball. Right? Can you tell me what your name is? Yeah. Louder. Kaustubh. Kharcha. Kaushik. Harsh. Okay, thank you. Now see, Siddha. He is associated with Harsh unless he goes and changes his name in future. But he is Harsh no matter what. So 100 grams is cricket ball, period. But if the same measurement gives me different answers, none of those answers can be associated with the system. Right? Supposing there are mental copies of say 20 people like him, and he says Harsh, somebody says I am Shyam, somebody says something, then none of these names belong to any one student because they are identical, but yet they are giving different names. Right? So therefore, when you have identical measurements on identical systems giving different results, okay, then it is very clear that any of those results, any one of those results cannot be uniquely associated with any system. Unlike in classical mechanics where the association is unique. So this also means that identical causes do not produce identical effects. So this means that quantum mechanics violates causality. Classical mechanics respects causality. Okay, there we go. So now there is something called repeatability and measurements. What does that mean? Supposing I measured the mass of the cricket ball. Okay, I measured the mass of the cricket ball. Okay, I measure it today, I measure it tomorrow, measure it day after tomorrow. So what happens? These are repeated measurements at later times. So today it was 100 grams, tomorrow it will be 100 grams, day after tomorrow also it will be 100 grams. So if I ask his name today, he says Harsh. If I ask his name tomorrow, he will again say Harsh only. So in classical mechanics, repeated measurements on the same system or identical system will give the same answer. In quantum mechanics, that's not what happens. What is it that happens? If I repeat a measurement, this is what happens. The first time I repeat a measurement, I don't know what the answer I am going to get. But supposing I get a particular answer. And once I have gotten the answer for a given particular system, and I make a measurement on it again, then I'll get the same answer. So that means I'm going to start getting the same answer from second measurement onwards. I cannot predict repeatability for the first to last measurements. So the first measurement is always random. We don't know what it will be. Okay? But repeated measurements after the first measurement has been done and I know its result, that is what is going to be repeated in subsequent measurements. Okay? So we say that when I first make a measurement, that is I make the first measurement, the system collapses into one of the allowed set of values. Okay? And once it has collapsed into that one particular number in those set of values, then that number continues to be associated with that system. Okay? So repeatability is possible from second measurement onwards. Many of these facts I am stating as facts. I am not necessarily will be able to prove it, but many of these are assumptions of quantum mechanics. So some of these don't have proof either. Okay, now this is something you must have done in your solution of problems. Energy quantization. In classical mechanics, the energy of a classical particle is continuous. There are no restrictions saying that this cannot be the energy, that cannot be the energy, and so on. It's continuous. Okay? So the energy of a particle can be 5 joules, can be 5.1 joules, 5.5 joules, square root of 3 joules. It can be any real number. Okay, there may be bounds on the energy value, but within that bound it is a continuous, rational, real number. Okay? Quantum mechanics, that's not what happens. If I have a bound quantum mechanical particle, okay, then the bound quantum mechanical particle cannot have any energy it wants. It has to have an energy that belongs to a set of values of energy. Okay? And these are called energy eigenvalues. Okay? I'll give you an example for this calculation. How do we find these allowed energy values? Well, you remember that I said that a particle is associated with the wave in quantum mechanics, and the wave is called the de Broglie wave. Okay, and now there is a relationship between the wavelength of this wave and the momentum of the particle. Okay, and what is that connection? That connection is that the wavelength lambda is equal to the Planck's constant divided by the momentum. And I hope you all know what is Planck's constant. Right? Planck's constant was discovered by Planck when he wanted to explain the black body radiation. So we know that we've got relations like E is equal to h nu and so on. So this is one of the other kind of relations where P is equal to h by lambda or lambda is equal to h by P. So if I want an integer number of waves to be fitted into the bounding region, so let us consider a particle in a box whose length is L, whose width is L, apologies. So then L must be an integer multiple of the wavelength. Okay, so if I do that, I put L is equal to n into lambda, where n is some integer. Then I substitute for lambda is equal to h by p. Okay, and what do I find? I'm going to find the momentum. So the momentum is given by, oh, I can see that. Well, I'll let you do the calculation. Okay, and then if I calculate the energy, the kinetic energy of the particle, which is given by half mv squared. So if I replace v is equal to p by m, so I'm going to get p square by 2m. So if I calculate p square by 2m, there it is. So p is equal to h by lambda, I square it, h square by lambda squared and 1 by twice m. And then I can substitute for lambda, I'm going to get n squared h squared by twice ml square. So I can find what are the allowed energy eigenvalues of a particle in a box by ensuring that the criteria for finding the allowed energy eigenvalues is that an integer number of de Broglie waves is fitted into the bounding region, the confinement region. Okay? So let's go to the next slide. There we are. What about the hydrogen atom? The hydrogen atom, there is an electron and a proton inside the hydrogen atom. The electron goes around the proton. Okay, I'm going to ask you a question. Why doesn't the proton go around the electron? Can somebody answer that question? Why does the proton not go around the electron? Any of you girls? Why is it always the electron that goes around the proton? Yeah? Now I want to point out something very important. Unless you think about what you learn, you are not going to go very far. So what this tells me, the total silence here tells me that you guys are not thinking, you're only remembering. Physics is not just a collection of facts. Physics involves understanding and application. So this tells me that the understanding coefficient is somewhat low. You need to brush that up. You cannot rely entirely upon memory. That is terrible. Okay? So the reason the proton does not go around is because it is 2000 times heavier than the electron. It is much easier for the electron to move around than for the proton to move around. Is that clear? Okay. In the same way, you've got electronics. But you don't have protonics. Why is that? Again, because protons don't move very much. You know, a fat man doesn't move very fast, but a lean man, he can run very fast. So electron is like this lean man, okay, and proton is like a fat man, okay. All right, so let me go on. So here I find that I can find the radius of the circular orbit of the electron, okay, and that is given by, what is that? You equate the Coulomb attraction to the centrifugal force, okay, and you can find out what is the radius of the electron, and I put 2 pi r equals n lambda because the circumference has to be now fitted with an integer number of de Broglie waves. So if I do that, then I can find out what is the energy, which is given by 1 by 4 pi epsilon 0. There is a minus QE square by twice R. Can somebody tell me why is there a minus? How can energy be negative? I need some answers. Somebody told me that you guys are among the top students. I'm trying to find out who the top person is. In fact, this should be answerable by everybody. The energy is negative because the particle is bound. Bound particles have negative energies. Unbound particles can have zero or positive energies. Is that clear? Okay, good. So therefore I find this is the expression for the energy simply that comes from the equation that says that the centrifugal force is equal to the Coulomb attraction. And then I can solve for the energy. Again, I will let you do the algebra and nobody will get the right answer. So it appears that one of the ways of deriving quantum results is to fit an integer number of de Broglie waves into the binding region. Here the binding region is the circumference of the orbit. Okay? And it turns out that it does give you the right answer. In the answer here there is E. E is actually the charge of the electron. In the earlier formulas I used QE. So QE is equal to minus E because the charge of the electron is negative. Okay? Alright. You must have all heard of the Bohr's quantization rule. What is the Bohr's quantization rule? One of you get up, be brave. I don't mind if your answer is wrong. But at least I want to see some confidence. Somebody gets up and says something. Okay, how about you there? Yeah, that's you. One with the tie, leftmost. 1, 2, 3, 4, 5. Fifth row. Yes, that gentleman. Yeah, okay, stand up, tell me. Yeah. What is the Bohr's quantization? Have you heard of it or you have not heard of it? You have heard of it. Then tell me what it is. You don't remember? Okay, sit down. Well, I'll come to that rule in a minute. But again, let me put a integer number of de Broglie waves inside the circumference. And I'm going to get 2 pi r is equal to n lambda. Substitute for lambda is equal to h by p. And then I can multiply by p on both sides and divide by 2 pi. I get p into r is equal to n into h by 2 pi. Now h by 2 pi appears very often in physics. And they have given it a new name and a new symbol. It's called h bar. So I write h and cut it. Okay, but I could not do that on the computer, so I have written h bar everywhere. Okay, but normally it is written by h with a cut on top of it. Okay, so what is p times r? P times r is the angular momentum of the electron in this orbit. And what do I find from this equation? I find that the angular momentum is equal to nh bar. So it means that the electron going around the proton cannot have any arbitrary value of angular momentum. It has to have one of allowed values of the angular momentum, and these allowed values are integer multiples of h bar. You can check h bar will have the units of angular momentum. What is the unit of h bar? If you look at E is equal to h nu, that tells me that h behaves like energy into time. And that also is the same as the unit for angular momentum. So many times these equations need to check to find out whether there is consistency as far as units are concerned or dimensions are concerned. Okay, so and this is the Bohr's quantization rule. So Bohr was able to derive his expression for the energy of the electron in the hydrogen atom by stating that allowed orbits have integer multiples of h bar as their angular momentum. This is the Bohr's quantization rule. And we have just derived the Bohr's quantization rule by assuming that an integer number of de Broglie waves can be fitted into the circumference of the orbit. Okay? Okay, the harmonic oscillator. The harmonic oscillator is what? Half kx square. That is the potential energy of a particle in a harmonic oscillator, and I've drawn several de Broglie waves corresponding to different energies. Now here U is positive half kx square, but if I wanted to construct a well out of the harmonic oscillator, I would have to move the zero energy right to the top. Okay? So when that happens, you'll find that there are small pieces of this wave going outside the parabolic line, okay, and that small part is because this harmonic oscillator has been moved above the energy is equal to 0. So we say that the electron inside or some particle inside the harmonic oscillator has a finite probability of tunneling out of the harmonic oscillator well. Okay? So but then let us try to see if we can find out the quantized energy values of the system using the technique that I mentioned. What is that? That there must be an integer number of waves fitted into the bounding region. So let us do that. We know that U of x is equal to 1/2 m omega squared x squared. Now you know that k is the spring constant, k is equal to m into omega squared. So what are the classical turning points? That means I draw an energy line and that's going to cut the parabola into 2 points. These 2 points are called turning points. That is, if a particle goes there, it has to return back, because if it has to go outside, then it would have to have a negative kinetic energy, which is not possible. Okay. So then what happens? I calculate the expression for the amplitude in terms of the energy, which is square root of pi c by n omega squared, where E is the energy and omega is the natural frequency of the oscillator. So again, let me now put an integer number of waves. So n lambda should be equal to a, but I am going to put a pi a here. Pi may be considered as a heuristic introduction. Remember, the rule that I am giving you is not exact. It's what is called as the rule of thumb. The rule of thumb means that in most cases it gives an answer very close to reality. In some cases it gives you exact answer. Okay? But here I need an extra factor of pi in order to get the closest answer possible. So I've got pi times a rather than a. So then what happens? I'm going to get that is equal to nh by p. Solve for p. P is equal to nh by pi a. And we require that that should be equal to 2n by lambda, because p is equal to n by lambda into h bar. And then I can put p is equal to, I can solve for p in terms of the energy, which is n h bar omega square root of twice m by e. But then I again substitute e is equal to p square by twice n and substitute for p. So then I'm going to find that e both in the numerator on the left hand side and in the denominator on the right hand side. So if I multiply through e, I get e square is equal to nh bar omega whole square, which means then that e is equal to nh bar omega. That's the quantization rule for energy values in the harmonic oscillators. I don't know whether you know this fact. Do you know this fact? Energy of a particle in a harmonic oscillator consists of equally spaced eigenvalues. So you can see that for the particle in the box, the energies were n square, they are proportional to n square. For the hydrogen atom, it was proportional to 1 by n square. For the harmonic oscillator, it is proportional to n. So equally spaced eigenvalues is found only in this system. No other system is going to give you equally spaced eigenvalues. Okay? Next. Disturbance and simultaneous measurements. So what happens is, supposing supposing I want to measure the position and momentum. So supposing I want to measure both position and momentum at the same time. Okay? In classical mechanics that is possible. So when I throw a cricket ball, okay, I know where it is at that position. And if I put two shutter cameras just close to each other, then it can find out how much time has elapsed when going from a small value to the other value. Okay, and I can find its velocity vector multiplied by its mass, I get the momentum. So both position and momentum are simultaneously measurable as far as a classical system is concerned, such as a cricket ball. But in quantum mechanics, that's not possible. Okay, what happens if I arrange to measure the position of a particle, then its momentum is completely uncertain. If on the other hand I try to measure the position of the momentum of the particle, its position is completely uncertain. Okay, so if, for instance, if I go back a little bit, I hope my host will be kind enough to allow me as much time as I want. Okay, you'll find that here, for instance, when they are behaving perfectly like waves, I can tell you where the position is. Okay, I can tell you where the position is. But when the particles are doing this, the particle can be either there, or in any one of those bright bands. Okay, so position is uncertain. But because I know where these bands are situated, I can find out the wavelength. So if I know the bright fringe and the dark fringe distance, I can find out what is the wavelength. Right? So there you go. I've measured a wave property, okay, from which I can find the momentum, because h by lambda is equal to momentum. So this interference pattern gives me an exact value for the momentum, but position is completely uncertain. In order to measure the position, supposing I make the particle fall into a photographic plate. So I can say, the particle is here. But what is its momentum? I don't know. So I can either know the position or the momentum, but never both at the same time. Okay? So if I make measurements of the system in one particular manner, and after that I do another measurement, it's quite possible that the second measurement can interfere or destroy the result of the first measurement. I'll explain a little more of this later on. Okay? We've done this, we've done this, we've done this, we've done this. Okay, harmonic oscillator also done. So that's why it appears that measurements can disturb other measurements in quantum mechanics. But in principle, in classical mechanics, I can carry out ideal measurements, that is zero error, without interfering with each other. Okay? A complete set of commuting observables. What does that mean? Okay, so supposing I'm trying to find out all possible observables of a system. Take a cricket ball again. I need to measure what is its position, what is its momentum, what is its mass, what is its energy, and if the cricket ball is spinning, what is its angular momentum, and if the cricket ball is moving around something, I can also find out what is the angular momentum, what is called as the orbital angular momentum. All of these quantities can be found, and each of them is an observable. So it turns out that I can measure any observable I want without error, okay, and measurement of one observable will not interfere or destroy the value obtained from a previous measurement on a different observable. But in quantum mechanics, that's not what happens. Let me tell you what happens. Supposing I wanted to measure, by the way, I should mention that the set of all possible observables for a given system is called a complete set of compatible or commuting observables. So that is generally labeled as CSCO. Okay? Whereas in quantum mechanics, we can have a set of variables which we call as canonically conjugate. So what about these canonically conjugate variables? Well, you can never know with great precision the values of both of these variables at the same time. That means canonically conjugate pairs can never be measured simultaneously with zero error. It turns out that measurement of one of these pairs will necessarily destroy or interfere with a previously made measurement on the second pair, on the second partner of that pair. So for instance, if I measure the position first, okay, I will have no information about the momentum and I cannot make a momentum measurement. Okay, supposing I make a momentum measurement, okay, then there is no way I can find out what a position measurement is. But I can tell you something about a very interesting effect as far as the two-slit experiment is concerned. What some people did was they said, okay, let me put a small detector near slit S1. Okay, then if the particle is going through slit S1, that detector is going to be triggered. So then I know where each particle went. So I'll be able to find out the trajectory. And lo and behold, when they did that, the interference pattern disappeared. All I found was two heaps. One heap of particles going through S1, another heap of particles going through S2. So what happened? I knew the position and the trajectory information because of this extra detector, but momentum is lost because I don't have interference effect. So the interference pattern is washed out if I try to find out something more about the particle during the experiment. Okay? This is the quantum world. So I think I sort of repeat the same thing over here, so we need not repeat this. So what happens is that whenever I am dealing with conjugate variables, I can do something with finite error. So let me say that I don't want to know 100% what the value is. If I can say that the value of position lies between, say, 5 centimeters and 5.1 centimeters, that means the error is 0.1 centimeters. So that means I have a finite but a non-zero error. In such a case, I can also measure the momentum, but it will also have an error. So let us suppose delta x is the error in the measurement of position, and delta px is the error in the measurement of the x component of the momentum. Then it turns out that the product of these two quantities, delta x and delta px, is of the order of the Planck's constant. Okay? And this relation is called the Heisenberg uncertainty relation. I don't know if you have heard of the Heisenberg uncertainty relation. Yeah, that's what this is. So delta x, delta px is of the order of h. But supposing instead of finding out the momentum along the x direction, I wanted to find the momentum along the y direction, whereas I measured the position along the x direction. Then it turns out that delta x, delta py is 0. That means that x and py are not canonically conjugate variables. So then I can measure either x or py with complete accuracy, 100% accuracy, zero uncertainty. Okay, and it will not affect the results obtained earlier. Okay. This is called the Stern-Gerlach experiment. Okay. So when I throw a cricket ball, the cricket ball could be spinning about any axis. The axis could point like that, could point like that, could point like that, could point down. Doesn't matter. And all of these orientations are permitted in classical mechanics. Right? So that means the orientation variable is continuous in classical mechanics. Remember that everything that is usually continuous in classical mechanics appears to be discrete in quantum mechanics. The same is also true for orientation of spins. So it turns out that the spins of particles can have definite orientations. So supposing, for instance, I have got a inhomogeneous magnetic field and I pass a beam of particles that have a non-zero magnetic moment. So before entering this apparatus, their spins could be randomly oriented and their magnetic moments are aligned along the spin or anti-aligned along the spin depending upon the charge of the particle. So then when it goes there, I know that when I place a point magnetic dipole in a non-uniform field, it's going to experience a force. Right? And that force is going to deflect the particle from the straight line path it is traveling. Right? And if the spin is up, it's going to be deflected in one direction. And if the spin is down, it's going to be deflected in the other direction. So what happens when I put a screen outside of these magnets? I'm going to get two patches if there are two possible orientations. If there are many possible orientations, I get so many distinct patches. But the point is that the number of patches is discrete. Whereas if these were classical particles, then what would happen? I would have a continuous distribution of spins and therefore these particles would be in a single hump. Okay, where most particles would be in the center and there would probably be some tails on the either side. Okay, so that is the key difference. So in quantum mechanics, spin orientations are discrete. So let me repeat this. So outgoing particles are detected by the, so I think I've mentioned this already. This is something very interesting. This is called the disturbance of earlier measurements. I also call them as incompatibility of spin vector components. Supposing I got a particle that is just entering, a beam of particle that is just entering SG1. What is SG1? Stern-Gerlach apparatus 1. And the arrow says that it measures spin along the Z direction. Okay, so it splits into two beams because one of them will have SZ in the positive direction, the other will have SZ in the negative direction. I take the positive beam only and then I orient a Stern-Gerlach experiment 2 perpendicular to the Stern-Gerlach experiment 1. So what does the Stern-Gerlach experiment 2 measure? It measures the X component of the spin. So whenever I do that, I again get two beams. So what does that mean? That means I should have XX is half in one beam and SX, that is spin in the X component, is plus half in one beam. Spin in the X component is negative half in the other beam. I again take just the positive one. Okay? And now mind you, when this beam is coming out, you would expect, classically at least you would expect, that the particles in this beam, which says Sx is equal to half, will have Sx is equal to half and Sz is also equal to half. Because Sz has been previously measured to be plus half. And I'm only taking the plus half part of the beam. Right? So that is what I would expect. I expect that its Sx and Sz values are fixed. Okay? But then let me pass the Sx is equal to half into a Z-oriented spin-Gerlach experiment 3. Then what happens? Again there is a split. Okay? There is no surprise in the split Sz is equal to half. You might say, oh well, that came in all the way from SG1. Because those particles had already been pre-selected to have spin up. But then where did this Sz is equal to minus half beam come from? Because we knew for sure that there were no Sz is equal to minus half in the initial beam. But there is an extra beam that is produced by Sg3. Where does it come from? Okay, this is true for classical particles. Sorry, my apologies. This is true for quantum mechanical particles. So what happens is that whatever value of the Sz I measured earlier and subsequently I measure Sx, then the information about Sz is completely lost. So when particles come out of the Sx measurement, there will be equal probability of spin up and spin down. So the previous measured value is lost. So we say that the Sx measurement is not compatible with the Sz measurement. So I cannot measure them one after the other and expect the system to have values corresponding to the results of these two measurements. Because one measurement destroys the results of the other measurement. Okay? So therefore, what do I find? I find that the various components of spin cannot be simultaneously measured. I can either measure Sx or Sy or Sz. All three cannot be measured together. So what does it mean? It means it is impossible to find out the spin vector of a quantum particle. For a classical particle, I can do that. But for a quantum particle, it's impossible to measure the full spin. What can I measure then? I can measure one of the components, usually that is chosen to be Sz, and I can measure the magnitude of the angular momentum. So it turns out that each of these spin direction values is compatible with the measurement of the magnitude of spin of a quantum particle. Okay? So, but then I cannot measure individual spin vector. I can't say where the spin vector is pointing. I don't know. All I know is what is its component along one direction and what is the magnitude of the spin. So the way people represent is by a cone. Supposing I know the value of the z component of the spin, they say that the spin vector is rotating about the z-axis. Okay, so that means the x and y components of the spin are changing always. I can never tell what it is. It could be anywhere on the cone whose axis is the z-axis. Okay? Alright? Okay, you must have heard of identical twins. Are there any identical twins in the audience here? No. But you have heard of the situation, right? You heard where two people look exactly alike, right? And you cannot tell them apart. Okay, and movies have been made, okay, highlighting this confusion and creating some humorous circumstances. Okay, so identical means that they look the same, but there is still some difference. If there are two identical girls, one is named Rashmi, the other is named something else. I can't remember. Rashmi and Reshma, let us say. So what happens is their names distinguish them. So these are identical people with something that distinguishes them, that is their names. So in the same way, in classical mechanics, I can have identical particles which are still distinguishable. In quantum mechanics, that's not possible. Identical particles are usually indistinguishable. You might say, what's the big deal? Whether I can distinguish them or not, why should it make a difference? Oh, it does make a difference. Supposing, for instance, I have got two states, okay, the states are S1 and S2, and two particles I am going to call A and B. So there are two possibilities, particle A is in state 1, particle B is in state 2. Or reverse, particle A is in state 2 or particle B is in state 1. So I can label these two possibilities by this combination, S1 of A times S2 of B. What does that mean? That means particle A is in state 1 and particle B is in state 2. But since the reverse is also possible, it turns out that I can write down the quantum mechanical wave function by adding the reverse possibility as well. So in quantum mechanics, I cannot distinguish whether particle A is in one state, in state 1, or particle B is in state 2, or vice versa. So these two options are indistinguishable. Okay? So therefore I can have what is called as a boson state and a fermion state. So in a boson state I got a plus sign. In a fermion state I got a minus sign. So therefore bosons and fermions behave differently. Bosons, where did the name come from? Does anybody know? One of you stand up and speak loudly. Who can that be? How about you? Where did the word boson come from? Louder, louder. Yes. Huh? Yeah, but what is his full name? Huh? Can't hear him. Can anybody tell? You tell? Someone called Satyen Bose. Not Jagdish Chandra Bose. Satyen Bose. Sit down. So this was given by Satyen Bose. And fermions. Okay, whose name comes up in the word fermions? Fermi, Enrico Fermi. He was an Italian physicist who migrated to United States, okay, and was responsible for their nuclear program. Okay? All right. Now you see, something happens for the fermion state. Take a look at the fermion state. Supposing S1 is equal to S2. What does that mean? That means particle A is in one state, particle B is also in one state, and these two particles are fermions. Then what happens? The first term in S fermion is identical to the second term in S fermion, and there is a minus sign between them. So what happens? They cancel out. And I am going to get S fermion is equal to 0. So that means the probability that two identical fermions are in the same state is 0. Because the state function, which is called S fermion here, is 0. So and that gives rise to what is called as the Pauli's exclusion principle. What it states is that two identical fermions can never occupy the same state. So once a particular state is occupied by a fermion, all other fermions are excluded from that state. That's why it is called the Pauli's exclusion principle, and it was enunciated by whom? It was Wolfgang Pauli. Okay, German mathematician, German physicist. I think you guys need to know a little bit of history of the subjects that you study. I'll talk a little bit more about that after the talk is over. Okay? So, where is the Pauli's exclusion principle useful? Everywhere. You can find the electronic configuration of atoms in chemistry, physical chemistry. You can also study to find out details about the theory of conduction, electrolytic conduction, electric current conduction, as well as even thermal current conduction. And it is also necessary to explain why electrons cannot be trapped inside the nucleus of an atom. Why is that? Why did anyone even think about this fact? Well, it turns out that in beta decay of unstable nuclei, electrons are produced. These are called beta particles. Okay? But then, so some people said, oh, maybe the electrons are contained inside the nucleus and the nucleus spits out electron. But it turns out that because of the Pauli's exclusion principle, there are a very limited number of states available inside the nucleus. And therefore, there is no room to occupy electrons inside the nucleus because of the Pauli's exclusion principle. So it is very important. Okay, there are some more interesting facts. I'll simply run through them. We are almost getting there. So the behavior of bosons is to aggregate together. Bosons are great at making friendships, whereas fermions, they want to stay alone because of the Pauli's exclusion principle. Okay, so although quantum mechanics applies to microscopic objects like electrons, protons, etc., the quantum behavior of bulk matter, the bulk matter is macroscopic. But it turns out that the bulk matter, some bulk matter, can exhibit quantum behavior because their constituents are quantum mechanical. I can give you some examples. The examples are superfluidity of helium. When I take helium liquid and drop its temperature to very low, suddenly it loses its viscosity. And it exhibits very strange effects, such as if I put liquid helium in a beaker and let it stand, then the liquid will automatically rise on the sides of the beaker and start to pour out. Right? Because outside the potential energy is less than inside. So it wants to seek the lowest energy and it can go up and down, no problem with it. Right? A classical liquid cannot do that. Okay? We also have superconductivity. You must have heard a lot about superconductivity. So there are certain materials which if you cool very much, suddenly you lose their electrical resistance. And then you can find that if I have got a superconducting wire and let us say I drop a magnet through it, then what happens? The induced effects of magnetic field set up currents in these coils. And if this coil is supercooled to become superconducting, then what happens? The current in this coil continues for years together. In an ordinary wire, what would happen? The resistance will heat up the wire and eventually there will be no current. But in a superconducting wire, what happens? Current will continue. No heat is generated because there is no resistance. And due to conservation of energy, current will continue in the circuit. Okay, so that is superconductivity. Fermionic constituents in macroscopic objects can also show quantum effects. Okay. So what are these things? Well, I can use the Pauli's exclusion principle and the quantum mechanical properties of fermions to describe the structure of atoms, structure of the nuclei of atoms. Now see, the nuclei of atoms contains neutrons and protons. Neutrons and protons are fermions. Okay, so therefore fermionic properties are important in understanding the behavior of nuclei. What about a neutron star? Has anybody heard of a neutron star? A neutron star has only neutrons in it. Why is that? Because it turns out that when there is an excessive squeezing due to gravitational fields, protons and neutrons interact with each other. Protons are converted into neutrons and they give out beta decays and antineutrinos. Neutrinos, I think. Yeah. And then what happens? The protons have been converted into neutrons. So everything becomes a neutron. And so you have got a large, very heavy binding of only neutrons. There are so many of them that they actually become a star. Their masses are much larger than the mass of the sun. That is how large they become. And the behavior of that star, mind you, nothing can be more macroscopic than a star, is quantum mechanical. So don't think that quantum mechanics is only for very small objects that I cannot see. Even for stars it is important. So if I wanted to find out what is the equation of state of a neutron star, I need to apply quantum mechanics to neutrons. Okay, so it is quantum mechanics of neutrons plus gravitation. Okay, so what happens before an ordinary star becomes a neutron star? When it suddenly collapses, the outer regions of the star are blown away, because the excess gravitational energy that is produced by the contraction is delivered to the outer layers of the star. And when that is blown away, intense light and heat is produced. So that if there is a supernova happening in one of the stars of a galaxy, then the light coming in from that particular star can be much more than the light coming from the entire galaxy. So a single star outshines the galaxy during a supernova. So how the supernova occurs, all of this can be described by discussing how fermions behave under intense gravitational fields. This is another very important thing. Non-locality and EPR paradox. So here, we are only discussing quantum mechanics. We have left classical mechanics by the wayside. So what happens here is, I've got these two particles which are close together initially, and you see they are going to have states like S boson and S fermion. These states are said to be entangled because they are made up of two different choices, which are the state A, the particle A is in state 1, particle B is in state 2. So then what happens? Each of these components is called a disentangled state. But a combination of the two states is called an entangled state. So it turns out that this entangled state system behaves like a single system. Okay? So it means that if one particle is here and another particle is there, and I hit this particle with a hammer, that other particle is going to feel the pain. The spatial distance is immaterial. I could have a particle here and another particle on the moon. No matter how far the separation is, whatever I do to one particle is instantly conveyed to the other particle. Now this is problematic because Einstein said that nothing can travel with infinite speed. Okay? All speeds are bounded by the speed of light in vacuum. This is called Einstein's theory of relativity, one of the fundamental postulates. It's also called Einstein's causality or Einstein's locality. Okay? So it turns out that quantum mechanics is non-local. It's non-causal, it's non-local. Completely destroys your common sense. I'll have one word to say about common sense in a little while. So there are many things to study in quantum mechanics, and I don't have time to do justice to them all. So Einstein's theory of relativity. All that I've been describing so far is the quantum mechanics of non-relativistic particles. But supposing particles are moving at great speeds, how do I describe the quantum behavior of these fast moving particles? Then I need something called relativistic quantum mechanics. It turns out to be very difficult to construct a consistent theory of relativistic quantum particles. Okay? So that is something to study and possibly even do research on. Okay? And measuring instruments, yeah. So quantum mechanics, let us say, applies to electrons and protons, etc. But then these electrons, protons need to be measured. So the measuring instrument is called classical. It's supposed to be classical. So there is an uneasy boundary between quantum and classical. Okay? And without this boundary, I can either not observe a quantum system, or if I observe the quantum system, I need to know how far down the line I should go before it stops being classical and becomes quantum mechanical. For instance, I can measure something and let us say that produces a current which passes through a galvanometer, and the galvanometer produces a deflection. Now I can see the deflection. So the deflection of the needle of a galvanometer is classical. But what is it that produced the impulse that made the galvanometer needles flip or change its position? It is the current due to the electrons. The electron is quantum mechanical. So here's the question. Where does the quantum suddenly become classical? Where is the dividing line? The dividing line is blurred. You cannot have one consistent description right from the measured object all the way up to the observed object. Some people carry quantum mechanics not just with the galvanometer needle. They say, I see the galvanometer in my eye and my eye is connected to my brain. Everything is quantum mechanics. I am also quantum mechanical. Right? But that is, I think, a little too extreme. Okay? I'll skip here some more. The limiting principle, like I said, in everyday world, we know how cricket balls behave. Okay? But cricket balls are made up of atoms and molecules. And atoms and molecules are quantum mechanical. So how can classical behavior be manifested by systems whose constituents are quantum mechanical? So there is something called a limiting principle that tells me when quantum mechanical predictions are almost like classical predictions. What are those limiting things? You first need a large quantum numbers. So if I look at the hydrogen atom and I keep increasing this n to say 100, 200, then the electron in the 200th orbit is almost like a classical particle. I can have large values of mass, momentum and energy. If you look at the energy of the electron, it is measured in electron volts. That is 10 to the power minus 19 joules. If I measure the energy of the cricket ball, that's of the order of hundreds of joules. So there is a huge difference, 20 orders of magnitude. Okay? So you need such large values for classical behavior to appear. So you can have a limit that says that quantum mechanics behaves like classical mechanics. And this limit is given the name called the correspondence principle. Okay, I think I've given sufficient time for various aspects of quantum mechanics. I hope some of you have been at least surprised and are probably eager to learn more about this. Okay, and I hope that has been of some help. I just want to make one quick comment on common sense. What is common sense? Well, we all grew up in the classical world. And Einstein once famously said that classical mechanics is the set of prejudices inside my mind until I reach the period of adolescence. Well, after adolescence, I'm going to study quantum mechanics. So my intuition is entirely classical. So learning quantum mechanics means that I have to build a quantum-like intuition. And that intuition is mostly built upon mathematics. So mathematics will be the guide that will produce the intuition necessary to study and do research in quantum mechanics. Thank you. I think with this I'll stop. If you have any questions, I'll be happy to answer.
Thank you very much, Dr. Kulkarni ji. He's a very close friend to me. Actually, he's a very good friend. He's actually been recently retired from IIT Bombay. He was head of the department electrical. He's super senior to me, but obviously he has been for last many years, around 8 to 10 times he has been a trainer, a mass trainer for orientation cum selection camp in physics, Homi Bhabha Center for Science Education. Pre-departure camp he used to be the mentor leader. He has been to Tokyo with Indian students. He was the leader. He was actually holding the position of leader for physics, for International Physics Olympiad. Last year, Vijay sir could not go, so sir went to Saudi Arabia with students from India as a student leader. We feel actually these kind of intellectuals substantially add value to our existing students, because let me tell you frankly, if you see the summit, recent summit, AI summit, every global CEO has mentioned that students should think out of the box. Most of the students these days are only going to IIT just for securing the job. But these kind of academicians like quantum physics, quantum mechanics, engineering physics, these are hardcore areas. Today also in the morning when we were watching this AI summit. You talk of Alexander, who has been recently hired by OpenAI researcher at a 1600 package. IIT Kanpur alumni, who has been recently hired, Tropik Bansal at package of 800 crore, who has also been Ph.D. despite doing his BTech Mathematics and Scientific Computing IIT Kanpur. In order to bring these type of people, these kind of intellectuals to our institution, Shraddha has been an open platform. Honorable A.R. Tambe sir is very pro for the interest of the students. He actually encourages these kind of people to come across. Sir is a very bosom friend of H.C. Verma sir, whom we interacted in recently concluded International Physics Convention in Goa. It was held in Goa University. We have invited Professor H.C. Verma sir also to enlighten our student. Last time, 2 more professors have come, enlighten our students. We are really honored and privileged, and sir has also come along with his mother, who is 87 years old, his wife. We extend our deep gratification to Honorable sir and his family, and we really keep looking forward for such kind of intellectuals across globe to come and enlighten our students, so that students also have great kinds of insight into not just IIT में कोई भी branch मिलता है, just embrace that branch and I start earning money. There must be vision towards preparation. We talk of many of the high level of intellectual students who have given insight into securing the branch. There is a student called Karthi Patekar. His AIA rank was 6. He has not taken CS. He has taken engineering physics. Then he did his PhD in statistical tools from Cambridge, and he is the current president of boss of DRW in UK, London. So students are actually taking a lot of insights into the subjects, simply abruptly students, because visionary students, every visionary students who has done excel in their academic career, they have done their PhDs from Ivy League universities, like Professor Kulkarni ji also as an alumni from one of the distinguished institutions from US. So I thank him and his family on behalf of entire fraternity of Shraddha Group. Thank you very much, sir. Thank you very much.